Somewhere right now, someone is settling onto a horse's back like it's nothing unusual at all. Most of us assume a horse's body was simply built for that job. But the wild ancestors of every domestic horse alive today never had a spine built to carry a rider. Some riders and welfare researchers take that further, arguing horses were never truly built for this at all. That question shapes how you read your own horse's back and movement under saddle. It shapes whether carrying a rider is something a horse's body can genuinely handle, not just endure. And it shapes how you feel about every single ride you've ever taken. By the end, you'll know what really happened to the horse's body and where the debate actually lands. Today, we explore the gene that made horses rideable. Here's the short answer. Horses weren't born built for this, but they weren't only trained into it either. Somewhere between those two extremes sits a real, documented biological event with an exact name and date. Scientists gave it two gene names, ZFPM1 and GSDMC. One is linked to a calmer temperament. Call it the temperament gene. The other is tied to the horse's very spine, the spine gene. Exactly how that second gene reshaped a wild horse's back into a weight-bearing one is coming in detail. But first, we need to untangle three very different moments in horse history that get mixed up constantly. Horse domestication is usually told as one story. It's actually at least three, and they don't overlap the way you'd expect. Story 1. About 5,500 years ago, the Botai culture in Central Asia was already managing horses. But genetically, those Botai horses were a dead end, not the ancestors of horses alive today. Story 2 starts later, around 4,200 years ago, in the Volga-Don region of what's now southern Russia. A single lineage called Dom-2 emerged there and within centuries replaced nearly every horse population across Eurasia. Essentially every domestic horse alive today descends from that one Volga-Don lineage. That 2021 discovery flagged two unexplained genetic differences in Dom-2, without naming the genes behind them. Story 3 is the 2025 study that finally named the temperament gene and the spine gene, ZFPM1 and GSDMC. Before we get into what those genes do, it's worth asking how we can date this so precisely. None of these dates come from guesswork. They come from ancient DNA recovered from horse bones and teeth found at archaeological sites across Eurasia. Each sample gets dated, then sequenced, then compared against thousands of other ancient and modern horse genomes. Combined with a molecular clock, the steady rate DNA mutates over generations. Dates can narrow to within decades. That's how researchers can say a variant was rare in 1 century and nearly universal a few centuries later. It's also how they catch a false lead, like Botai, before it gets mistaken for the real ancestor. With that timeline in hand, we can finally explain what the spine gene actually does. First, the temperament gene. About 5,000 years ago, the temperament gene came under selection, linked to lower anxiety and a calmer nature. How it works at a cellular level isn't fully worked out yet, only that the link is real. That calmer temperament came first. The gene that rebuilt the spine came centuries later, around 4,750 years ago. Right inside that genetic bottleneck, the spine gene came under intense selection. By about 4,150 years ago, the variant had reached near fixation in that lineage. The spine gene's genotypes are linked to body conformation and spinal anatomy in horses. Weight-bearing conformation is the technical way of saying a back built to carry sustained load evenly, not just occasional pressure. In mice, the same gene region is tied to spinal anatomy, motor coordination, and muscular strength. So researchers didn't stop at correlation. They engineered mice with the spine gene's region altered to test it directly. Those mice showed measurable changes in spinal curvature and structure, and their forelimbs grew measurably stronger. That's causal, not just correlational. This gene region physically reshapes the spine and strengthens weight-bearing limbs. In other words, a rideable horse's back isn't just a wild back that got used to a saddle. It was reshaped at the genetic level to bear weight at all. The intensity of that selection is what stands out most. Horses carrying the spine gene variant left an estimated 20% more offspring on average than horses without it. 20% more offspring sounds modest on its own, but compounded generation after generation across a few hundred years, that's enough to push a rare variant to near universal. Some of the researchers behind this work have pointed out just how contingent that timing really was. A slightly different mutation in a slightly different population, and this whole timeline could look different. Researchers have compared it to a famous human mutation, lactase persistence, letting adults digest milk. That trait took far longer to spread through humans, even with an obvious survival advantage. The horse version swept through in a matter of centuries. Across the genome, researchers analyzed roughly 260 markers to trace exactly how and when this happened. Curiously, variants near this same gene in humans have been linked to spinal structure and back pain. That's a passing coincidence worth mentioning, not a causal connection to the horse story. This sweep wasn't the whole story either. Roughly a dozen more mutations show up later in history. One more relates to docility. Others, from the Iron Age to the Middle Ages, track increasing body size. The Rideable horse is a multi-thousand-year layered project, and the spine gene sweep is its most dramatic, best-dated chapter. The paper that identified the spine gene carries a telling subtitle, Implications for Human Mobility. Once a horse's back could reliably carry a rider, distance itself changed meaning. A trip that once took days on foot could take hours on horseback. That's not incidental to the Dom-2 lineage's rapid spread across Eurasia. The two are tangled together. Faster movement meant faster trade, faster contact between distant cultures, and faster, more mobile warfare. Historians already knew mounted horses reshaped trade routes and conflict across the ancient world. What this research adds is the biological trigger underneath that shift, arriving in just a few centuries. None of that mobility was possible until a horse's spine could reliably take the strain of it, day after day. That's the quiet biological footnote underneath a very loud chapter of human history. A single gene didn't just change horses, it changed how far and how fast humans could go. So what does this actually change for the person holding the lead rope? Mostly it reframes things. Carrying weight isn't a generic big, strong animal default. It's a specific trait built by intense human-driven selection inside a window of only a few centuries. So go back to that argument we opened with, were horses ever really built for this? The honest answer, not originally. The wild ancestral genome didn't carry this variant at meaningful frequency. But it's also not fair to call the modern horse's back purely trained or purely forced. It's a real biological adaptation, just an unusually recent and intensely human-driven one. That doesn't settle every welfare question about weight, fit, or individual horses that riders still raise. What the genetics do settle is simpler. This wasn't nothing and it wasn't everything either. Riders and researchers can keep debating the details. The genetics just changed what built for it actually means. So the next time someone swings up onto a horse, there's more happening than muscle and momentum. You're watching the endpoint of one of the fastest documented sweeps of a beneficial mutation in evolutionary biology. A horse's back carrying a rider isn't an accident of size. It's genetic history, written into every stride. I've watched countless people climb onto a horse without a second thought. Now I don't think I'll ever watch that moment quite the same way again. If this changed how you see a rider settling into the saddle, subscribe for more science like it. New videos on the evolutionary science behind horse behavior every week.